So this is basically one of the main topics that we started last time. And the idea is we want to test a general linear hypothesis. A general linear hypothesis is something like testing, for example, these two equations simultaneously, if you remember, in the context of regression, and we know how we can test individually each one of them. And it turns out that, so if you do something like this, you can do the t-test, but you have to account, so separately you can try to test whether this one works or whether that one works. Whether to reject this hypothesis or whether to reject this hypothesis, we can separately try to test. And if we reject either, then we reject this null. So the probability that we reject let's say, joint hypothesis is the probability of the union of rejecting either of the two individual tests, and there is an upper bound on this, which is called the union bound. The probability of a union of two events is the probability of the sum of the probabilities, bounded, upper bounded. And so if you want to control this probability, which is going to be under the null, this probability would be the type 1 error. So if you want to control the type 1 error, you can control these individual probabilities half the value that we usually need. So if you want to test at level 0.05, you try to test individually at level 0.025, so more stringent tests. And then this guarantees that under the null, so the null for this joint hypothesis would be the null for either one of them. So under the null, these would, individual ones are guaranteed at those levels, and so the sum would be guaranteed to be less than or equal to 0.05. Okay, so this is doable. So based on the t-test, like two t-tests, you can do this. But you can see if you have more than two constraints, so I have like beta 1 equal to beta 2, beta 2 equal to beta 3, let's say I have a bunch of more of these, okay? So let's say I have 10 of these conditions, then I would have to divide 0.05 by 10. So I have to like test individually at level 0.005, which is very strong. And then you could ask whether there's a better test. So whether we need to, so this bound is ignoring. So there is like, anyone knows what the actual value is? PA union B, for one like an exact expression? Yes.
PA plus B minus P of both.
Yeah, so P of A plus P of B minus P of the intersection. So the actual false positive rate would be smaller, but I can't control the intersection because these are independent and it's not easy. Okay, so we can come up with like a better procedure that like from the start controls the type 1 error nicely, and this test turns out to be more powerful. So the issue with this procedure is you're going to control the type 1 error, but because you're so rarely reject, even under the alternative, you're not going to reject. So your power or type 2 error is going to go, power goes down, type 2 error goes up. So this leads to this idea of trying to come up with a better way. To introduce a better way, let me just introduce some notation. First, let's say I have this regression problem, and I want to do this hypothesis test. Now I've changed the instead of like beta 1 equal to beta 2 and beta 2 equal to beta 3, I've written a different hypothesis. This is also an example where we can do this. It's an example where we have a bunch of linear constraints on the parameters. Okay, so here we have two. You can write it in this format. If you think a little bit about this, these two equations, I can write it in this form as a linear system of equations, A times beta equal to 0. Okay, and there are different ways of writing a set of constraints like this. And what we care is we want the number of constraints basically be less than or equal. So the number of constraints we're going to call Q. This side is going to be P plus 1. So we're going to assume that this Q is less than or equal to P plus 1. And we want to require that the rank of A is Q. So A is full rank. Okay, full A or has full row rank. So the reason why we want to do this is that if this happens, then the constraints are linearly independent. Okay, I don't want to include like extra equations that I don't need. In this case, for example, if you add like, you could have added like beta 1 equal to 0. Okay, I could have added, so this is equivalent to beta 1 equal to 2 beta 2, beta 0 is equal to 0, and beta 1 is equal to 0. So this would give me three equations. I can write it as 1, 0, 0, and then 0, 0, 1, right? Beta 0, beta 1, beta 2. And then you might imagine, oh, I have three constraints here. I can also reorder things. So for example, I can switch these two rows. It just switches the order of the constraints. It doesn't matter. So first you can see that A is not unique in many different ways, but this we don't want to do. Why we don't want to do this? Because the constraints are not linearly independent. So one of them is redundant. So if I have these two, then I have this. If I have these two, I have the middle one. So I can drop one of them. I can drop this. If I drop this, it's a different set of conditions, but I can keep this and this, or keep this and the other one. So I can, for example, so if you look at this, the rank of this is not going to be 3. Right? The rank is going to be, is this correct? Did I write it correct? Well, beta 1 is not that. Beta 1 is, this is beta 1. Oh, okay. This is not quite correct. This is not a good example. So this we can't. These are not equivalent. Yeah, this was a bad example. Forget about it. This wasn't equivalent because I thought that was okay. This was beta. If it was beta 1, yeah. So let me do that. So suppose this is actually not. So if you have, this is a different set of constraints. This is not true. So this actually would be 1, 0, 1, negative 2, 1, 0, 0, 0, 1, 0. This is actually okay, and this is a different set of equations. This is a different constraints. So you can see that actually the rank is 3, right? So these are linearly independent, and it's actually like is equivalent to beta 1 equal to beta 0 equal to beta 1 equal to beta 2 equal to 0. Okay, so this I can write as, for example, 0, 1, 0, 0, 0, 1, 0 times beta 1. So these are equivalent, okay? So A is not unique. In this case, I can't drop one of them because that would change the constraint. So, okay. So the point is we want so the linear constraints that are linearly independent. Let me give you an example where things are redundant. Maybe I'll give it to you later, but so you can imagine you could add more constraints. So if in this case, for example, I can add like, so let me do this separately somewhere. add. So these are equivalent, but for example, this is also equivalent to, I can have like beta 1 equal to 2 beta 2, beta 0 is equal to 0, beta 1 is equal to 0, and beta 1 plus beta 2 is equal to 0. So I can add these 1, negative 2, 1, 0, 0, 0, 1, 0, and then 1, negative 1, let's say. Beta 0, beta 1, beta 2. So this is equivalent because, for example, these imply that. But this is not, here sort of is the version that I don't want. So Q, it looks like Q is 4 here, but these are not linearly independent. So for example, if I can combine these two rows and get the last one. So the rank here is, so 4 by 3 matrix, but the rank, but not whole row rank. So you drop enough constraints so that you have equivalent set of constraints, but the row rank is, it's full row rank, okay? Sounds good. Hopefully correct. Let me do another example. So suppose you have H naught is example 2 or 3. This is example 3. Example 2. This is example 1. So example 3 would be like beta 1 is equal to beta 2 is equal to beta 0 is equal to beta 1 is equal to beta 2. Not equal to 0. Just they're all equal. So how many independent constraints do we have here? So we have 3 coefficients, beta 0, beta 1, beta 2. And this is my null. Yes.
2.
2.
They should be third one.
Great. Yeah. So this would be, for example, equivalent. I can do it differently. Like beta 1 is equal to beta 0. Beta 1 is equal to beta 2. That's one way of writing it. Okay.
Third one, if you wrote beta, they're only limited to that should apply.
If I write this, then yeah, so this is implied. But I can, for example, write something like that, and then beta 0 equal beta 1. That's another way of writing it. So if I do this, what would be my A matrix? A matrix. Right. Yes.
So the one on the left, you have 1 minus 1 0 negative 0 1
You don't need the last one. Yeah. So it just has 2 rows. So full row rank Q is 2. Same goes here. Q would be 2. Or we just that one. For the other one. 1, let's say 0, negative 1. 1, negative 1, 0. That's possible. Or I can multiply everything by negative 1. Right. Just for fun, let's do it this way. Okay, this is also valid. So you can see it's very non-unique. And so these represent the same problem. Okay, they describe the same set of betas. Okay, the thing is, the collection of betas that satisfy this is the same as the collection of betas that satisfy this. Okay, and they're all in this line, and this line in R3. If you plot the R3 space, the location of this is this line that passes through, it's like 1, 1, 1, and origin. Okay, so there's this line. So on this line, everything is equal, all the coordinates. And so that's the location that this parameter is assumed to be geometrically. So you can describe it as a set of different equations, different A's, but the betas, the set of betas is the same. Okay, we care about the set of betas, not this representation. Okay, sounds good. Are we good? Good, not good. So let's try to build a test. It seems like you're okay. So we're going to work with this setting. So if I want to represent this set of betas in our tree, oh, sorry, beta 1, beta 2, beta 3. Anyone knows what this set would look like? Oh, okay. We have like 0, bad notation, beta 0, beta 1, beta 2. Same goes here. Start from 0. Beta 0, beta 1, beta 2. So what is this set? Yes.
So that one just go subspace.
The whole subspace? No. The whole subspace means the whole space. The whole space, there are betas for which beta 0 is non-zero. So beta 0 has to be 0, so I have to be in this plane. And in this plane, I have beta 1 is equal to 2 beta. So it passes through, like if I have 2 here and 1 here, so it passes through this line. So the line here in this plane. Okay. If you have 1 constraint, it would be a hyperplane. If you have 2 constraints, it would be a line. If you have 3 constraints, basically it would be a point. And usually that point is going to be the 0, 0, 0, like origin, because these are homogeneous equations. You could have non-homogeneous equations, but mostly we're talking about homogeneous equations. Okay, so geometrically we care about this location. So how do I test actually? So what do you guys think we should do? What is a good test? So I can fit the original regression problem. I fit the original regression problem. And I get a mu hat, I get an E squared, like standard, sorry. We'll call it sum of squared errors, SSE, norm of E squared. That tells me how well sort of I'm doing in a sense. So what else can I do if I want to like test this hypothesis? Anyone has any guess? Have you seen anything like this before? Have you seen the F-test before? So what is the F-test? Can we do an F-test? So what is the F-test?
Divided by this bigger freedom over SST.
Oh, okay. SSE divided by the degrees of freedom, and then divided by SST divided by the degrees of freedom of the SST. So that's a particular F-test. So we'll see that that one is testing a particular hypothesis. Anyone knows what kind of hypothesis that one does? That will test beta 0. So that will actually test in this case. In this case, it would be equivalent to the t-test. So suppose I have something like this. Beta 2x2, beta 3x3, up to all the way beta p xp. So that one, SSE divided by degrees of freedom divided by SST divided by degrees of freedom is going to test whether all of these coefficients other than the intercept are equal to 0. Okay, so they call it testing for the significance of the linear relation. We'll see that that's a special kind of this type of test. You test whether all these coefficients are 0 except the intercept. But you can use a kind of f-test for this general problem. Okay, if you understand why that works, then you can also like work out this version and also this kind of test and any kind of linear set of equations that you have as a constraint. So if I want to explain why that works, what happens effectively in that f-test that you know, let's say SSE divided by the degree of freedom divided by SST divided by the degree of freedom. SST there is a particular SSE. It's like the sum of squares of errors of a particular model. Anyone knows what? So SST is the like basically y minus the mean of y. So we'll see that. So SST is like summation yi minus the mean of y. I from 1 to n. That's called the SST. SSE in the regression would be like I minus n. What would be the SSE? It's just basically the sum of squares of errors, right? Y minus mu hat I. So that y bar is actually mu hat of a particular model. So that's really an SSE of a particular model. Anyone knows? What model should I fit such that my mu hat I is just y bar? The model is y is beta 0, beta 1. So the model that you fit for which the SSE would be SST is the model that you set all the betas equal to 0 except the intercept. So if you just fit a linear regression with just the intercept, the best intercept would be just y bar. So you can calculate it using the technology that we have. So in fact is the, so I'm going to put a 1 here. As a vector would be beta 0, 1, beta 1, x1 plus up to beta p, xp. So this is in fact is the SSE of this simple model. Y bar is equal to beta 0, 1. So if you fit this, beta hat would turn out to be like beta hat OLS. Is X transpose X inverse X transpose Y. So 1 transpose 1 inverse, this would be like n. So you get 1 over n summation yi from 1 to n. So expected, what you expect is if you fit this, beta hat would be just y bar. Okay, and then this would just be yi minus. So mu hat would be just mu hat would be just beta hat 0, 1, which is just beta hat 0. Beta hat 0 would be y bar 1. So all the fitted values would be just y bar, constant. And so that's really SSE of this simple model. So what we're doing in the f-test is compare the SSE of the full model to the SSE of the reduced model. Reduced model as a plane by setting all the constraints that you want to test. So you want to test whether all the betas equal to 0, you set all the betas equal to 0 and fit that reduced model. And then you have the full model that like all the parameters are free, and then compare the SSEs, just the ratios of the SSEs. Okay, so the f-test really comparison of two models, why are there errors, basically, the sum of squares of errors. Does that make sense? You know, if you know the f-test as this, that SSE divided by, I'm not going to write the degrees of freedom, we'll see. but this divided by its degrees of freedom, and then over this divided by its degrees of freedom, then what you're doing is basically forming the ratios of two SSEs, one for the full model, the original regression with no constraints on the parameters, and one for the reduced model where we introduce like explicitly our own constraints and then solve. So a reduced form of reduced model. Questions? Where you set beta 1 equal to beta 2 all the way to beta p equal to 0. So call this M0. Sometimes I call it M0. So we have the full model, which is M, and then we have the M0 model where we set all the betas equal to 0 except the intercept. So M0 is a special case or a submodel of M. Questions? So we'll see these ideas, yeah.
So if you were to, in order to find the reduced model, when you say set all the betas equal to 0, like if you had X and Y, what exactly does that mean? Set all the betas.
So when I said all the betas equal to 0, I'm assuming a new model where yi is only affected by this and not the other covariates. So that model is a new model in which I assume that none of the covariates are.
X matrix stays the same, or would you?
No, the new X matrix basically here is just 1.
Just a column of 1. And
yes.
A bunch of zeros.
Doesn't make sense. I mean, you can have a lot of zeros, but you can just drop the zeros.
So if you just have 1, won't you get the same thing for the intercept every time, or?
So if you have this, once I set all of them equal to 0, I get this, and the intercept would be just, you can do this, like X transpose, so this is going to be my X. This is going to be my X matrix. Yeah, column of 1, n by 1. And so you get X transpose, X inverse, X transpose Y. So this is just n, because like
that will result in just one scalar value.
One scalar value, which is going to be just the sum, because this is like, if you think of this just sums all the elements of Y. This is dividing by 1 over n, so you just get Y bar. So if you fit a regression with just the intercept, you always, this turns out to be your estimate of the coefficient turns out to be Y bar. Right? If you add more covariates, this is going to be different. But in the case where, so this beta hat 0 here, beta hat 0 estimate here is different than beta hat 0 that you get when you fit the full model. But if there are no covariates, this is always going to happen. Just this little line of proof. Okay. So taking the average is actually like doing OLS in a very simple regression model. So averaging is that. So you can reduce all your t-tests or things that you have learned about. We'll see. Like comparing averages is basically fitting a regression model. Any other questions? So the thing is, this is a very particular hypothesis that I'm testing. I'm testing this null hypothesis. If I'm doing this type of F-test, let's say, we'll see. Effectively, what I'm testing is whether all these other betas are equal to 0 in that full model. But I can ask, for example, something else. I can ask to test, for example, I can try to test this. So how can I like do that principle? How can I generalize it to something like that? So I want to do this test. What will be the reduced model? So the reduced model is a model in which I enforce the constraints under the null. So how do you enforce these constraints to get a reduced model? One of them is really simple. Yeah.
Well, since beta 0 is 0, you can just take that.
Yeah, I'm just going to set beta 0 equal to 0, so this is going to go away. So how to deal with the second one, like the first?
And just substitute 2 beta 2.
Great, so I can like eliminate one of them, so I can, for example, substitute 2 beta 2 for beta 1, and then everything would be in terms of beta 2. So what I'm going to do to avoid confusion, Because actually this is good, but I mean, it's like I'm gonna name beta 2 here is gonna be like gamma, let's say, or let's say what did it, yeah, okay, so let's do this. So okay, let me try what you said first. So Abel so suggested that we do set beta 0 equal to 0 and set beta 1 equal to beta 2, and then beta 2 will be free. So our model would be y equal 0 times 1 plus 2 beta 2 x1 plus beta 2 x2 plus epsilon. Okay, and then so this is good because this will eliminate the constraints, and I don't lose anything because this has to be like that, and beta 1 has to be equal to this, and then beta 2 could be free. So in this new model, beta 2, there is no constraint on beta 2. Sometimes I might call this beta 2, let's say one of the one that I want to keep free, gamma, and then beta 1 would be 2 gamma, so that this is a new parameter so that I don't have to worry confusion with the original parameter. But we can just do beta 2. This simplifies further. Okay. How does it simplify? So I can just drop the 0, right? And then what happens is I can combine these two. Or we'd call this gamma. Okay. So these, because beta 2 is the same, I'm going to factor it out. And you can see this is a very simple regression. It's like a simple linear regression with no intercept and one covariate. The covariate is the combined covariates that I got, like from the interaction of the constraint. And so this is a new covariate. I'm going to call it Z. So the reduced model is just y equals z gamma. Or you can see, yeah, this is z gamma plus epsilon. So this is now your new design matrix. This is your x. It's one covariate. And there's one parameter, 1 by 1. So this new covariate is just 2x1 plus x2. Okay, so you fit this new model. This is the reduced model. And let's say M reduced. You can fit this. How do I fit this? Usual OLS, right? So you get gamma hat is equal to Z transpose Z inverse Z transpose Y. And then SSE of this reduced model, M reduced, would be just norm of Y minus mu hat. Mu hat would be just gamma hat times Z, or Z gamma hat if you want. X beta basically. So that's your SSE. This is the residual, Y minus, this is the fitted value vector. And so you get the SSE of the reduced model. So you have also the SSE of the original model. So compare to the SSE of the original model. M is this guy. This would be like Y minus X beta hat, where beta hat is just X transpose X inverse X transpose Y, where X is just 1, X1, X2. Okay, so I fit this full model. I have the SSE there, which is just the residual sum of squares. And the other one has the SSE of the reduced model, and then I compare them. Okay. So what we want is how much. So this, it turns out that this is going to be all. Which one is going to be smaller, do you think? Which SSE is going to be smaller? Let's go back here. Which of the SSE and SSD would be smaller? So SSE would be smaller. So SSE in general tells you like how well you're fitting. So the smaller it is, the better is your fit. So this model, this is, if you remember, this is the SSE of that simple model. That simple model is not going to fit very well. You're just comparing y to its average. This is like trying to explain more. So you'd expect that this is going to be smaller than this, and this is always going to happen. I'm going to like, hopefully by the next couple of lectures, you have a very intimate geometric understanding of what is going on, why this has to be smaller than this. And the difference is actually the amount that the full models explains over the reduced model. The same happens here. Whenever you have these models I'm going to call them nested. So this model, reduced model, is a reduced version of this. It's nested inside that, in the sense that if I like put constraints on the parameters, I get the reduced model. Because this model is nested within this model, the SSE is always going to be less than or equal to that. So a reduced model can't explain better than the full model, in a sense. So I know that SSE of the reduced model is going to turn out always less than or equal to that, unless you have rounding errors in which it might be bigger, but that's another like mistake. So if you turn out like do this turns out to be smaller than this, there's something wrong. Exactly as the thing that we discussed of y, normal y squared has to be like bigger than the normal fitted value to the SSE. So this is going to be always bigger than this, unless you have made a mistake or rounding errors. How much it is bigger tells you whether you want to reject your hypothesis or not. So if this is slightly bigger than this, it means that the full model is not explaining much over the reduced model. Then I'm going to go with the reduced model, which is the null hypothesis. If the difference is very large, then it means that if I include, like, remove the constraints, it's a much better fit. So we reject the null. So the constraints are not good. Okay. So we reject the null. So we always have, since M reduced is a nested model, or within M or of M, in M, we always have SSE of M reduced bigger than or equal to SSE of M. So we reject the null if this SSE, the reduced model, is much bigger than SSE of M. Okay, so this notation means much bigger. Just bigger is not enough. It could be slightly bigger, but we want much bigger. Okay, so whenever I have much bigger, then you'd ask how much bigger. Okay, and that's the job of statistics, classical statistics, trying to figure out how much bigger. Okay, how much bigger should this be such that under the null, I'm going to reject at most 0.05. Okay, I can be very strict, never reject. So this would be very, 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 very large. First, I don't know the scale, so I don't know how, like, what should I compare to? Is it like by a factor of 2 or by a factor of 10? Well, what does it mean to be larger? And also, like, I don't know how to set the threshold. Basically, you want to reject when this divided by that is large. Larger than 1, larger than 2, larger than 10. I want to set that threshold, but I want to set it so that under the null, you expect this, they're all about the same, but because of the randomness, they're not going to be exactly the same. I want to set it so that under the null, like 5% of the time I reject. Okay. So that leads to trying to come up with the distribution of the ratio. So basically we reject if SSE of M reduced divided by the SSE of M is much bigger than 1, but where do we set the threshold? For that, I'm going to have to try to figure out what the distribution of this quantity is under the null. set the threshold so that we have a test of size or significance level alpha, i.e. we reject H naught alpha percent at most at most 5% of the time under null. Okay, to answer this, we need to figure out the distribution of SSE of M divided by SSE of M. And if you properly normalize this, this turns out to have an F distribution. Okay, proper normalization is I have to divide this by the degrees of freedom and this divided by degrees of freedom, then this would have an F distribution. We'll see. Turns out that after proper normalization, I'm going to call it F hat. F hat, it's not F hat, let's say F tilde. F hat will be the properly normalized, and F tilde will have, after proper normalization, F tilde will have an F distribution. F distribution under null. Okay, so that's the story that we want to like figure out. So that's just the plan. Sounds good? So this works for any sets of linear constraints on beta. You just try to eliminate the constraints. You get a reduced model, fit the reduced model, and then calculate the SSE of the reduced model. And SSE of the reduced model divided by the SSE of M, how big it is would be your statistic. Basically, this is a test of the statistic that you consider. Okay. Gives you a very nice, simple way to test many different hypotheses. Questions? Okay, so a couple of points is that it's not always possible to do this elimination. In this course, it's going to be, but in practice, if you have a very complicated set of constraints, you can try to solve the OLS under that constraint. So you can solve the constraint least squares problem. It's equivalent to what we did here. So you can eliminate the constraint if possible. You can always do that using linear algebra. I'm not going to go into that. You can always turn this set of constraints, which is like A beta equal to 0, equivalent can be written as beta is equal to V times some gamma vector, where you have to calculate. So this is the dual version. If I can write beta as some matrix V times some vector gamma, then I can plug in beta there and then eliminate the constraints. But this procedure of going from this to that is a linear algebraic operation. It's like a dualization, like a dual type problem. The first one is saying that beta is in the kernel of A. The second one is saying that beta is in the image of V. So beta belongs to the kernel of A, can be written equivalently as beta belongs to the image of V. But you have to determine this V from A. Here, basically, we have determined it. So you have determined here that basically, in this case, beta, we've written it as this Z gamma. So this Z turns out to be that V. Okay, but in general, it could be like more, has more columns. Okay. If you can't eliminate, you can just solve this problem under this constraint. So least square, go back to the least squares optimization problem, you can just solve it using a numerical solver. Given that, and then everything else would follow. Once you have beta hat, you can plug it in, like you get the residual, everything is the same. You just have to find the right fit. Okay, that was one point. In this case, if you go through this example, I actually eliminated them differently. So in this case, I called beta 1 alpha gamma, and I got that beta 2 is gamma over 2, rather than calling beta 2 gamma. So this is okay. So in this case, you get a different z, instead of getting like x1 plus 2x2, which we got here. Sorry, we had 2x1 plus x2, right, because of the way I eliminated. In that case, we get x1 plus x2 over 2. So this is a different provided, different matrix. This gamma would be different. So when you fit, gamma hat would be different. Your matrix would be different, but this times gamma hat, so the fitted values would be the same. The SSE would be the same, and the test would be the same. So you could have a different way of reducing the model. The parameter estimate would be different, but the fitted values would be the same. The SSE would be the same. The test wouldn't change. Okay, so there's this freedom in doing this. Okay, just want you to like maybe contemplate this a little bit. The reduced model for us matters as far as this part goes. So if you remember, the original regression is y equal x beta plus epsilon. The real thing is that this we called mu, this belongs to the image of x. And this is what matters for us. The way that we model the regression is saying that the mean of y belongs to the image of x. Okay, so I can reparameterize, but mu is going to remain in the image of x. In the reduced case, reduced model, I would have beta. Let's say I can write it as v. Okay, so let's call it z gamma. It's actually better to call it z because I usually do z. So let's call this capital Z would be like a new matrix. Z. So if this is like Q by P plus 1, anyone knows what the dimension of this would be? And Q is full rank. So I'm going to call this D. D is going to be P plus 1. To compare with this, you see here we have Q is 2, D is 3. So Z would be D by, in this case, 1, but in general it would be like D minus Q. And this would be D minus Q by 1. So in this case, Q is 2, D is 3, so you get 1. Okay, so the dimension of the new parameter, free parameter, would be D minus Q. The number of the dimension of the original parameter, which is P plus 1, minus Q, which is the number of free, like the independent constraints. So this will happen. So we'll have this, where this is like, so this is D by 1. This is N by D. This is D by 1. Here, this is going to be D by 1. This is going to be D by P minus Q. D minus Q. And this is going to be D minus Q by 1. So basically, so you have D degrees of freedom in the original parameter. You put Q constraints, you reduce the degrees of freedom by Q. So your new degrees of freedom is D minus Q. This is not the degrees of freedom SOC. This is just the degrees of freedom in the parameter. Okay, the parameter used to be free in all the D directions. I put Q constraints on it. Now I have D minus Q degrees of freedom left. And so this is going to be reflected here. And because I have to like BSZ gamma, it would be like D times D minus Q. If I plug it into this regression, I get XZ gamma. That would be my reduced model. So now this is going to be N by D minus Q. And this is going to be D minus Q by 1. Okay, so that's the reduced model. So the way I write it as Z gamma would change, but this XZ gamma is not going to change. So this is going to be this is going to be my mu. We're going to call this mu of A. A for the, because of that A matrix that we had. So A beta equal to 0 is equivalent to this. Your book calls it mu of A or mu hat of A. So this belongs to some space which is image of xz. And this xz is going to, the image of xz is going to be invariant to how you reparameterize. So for example, in this case, the image of this would be the set of all vectors that are in the same direction as this. So if I multiply this by 4, it's on the same image and I get the other version. So the image of like 2x1 plus x2, so the image of 2x1 plus x2, that was our original formulation, is the same as the image of x1 plus x2 over 2. So the image of the reduced design matrix is the same, no matter how you parameter. So your new design matrix is going to be xz. The image of xz is going to be invariant to parameterization, and this image is a subset of Rn. This is a subset of Rn, and it turns out that this new subspace is going to be inside this guy. Okay, so your book writes this as L of x. If you have seen it, this one it writes as LA of x, which I use in the slides. But if you use this dual notation, it's just the image of x times z. It's your new design, the image of your new design matrix. Okay, a lot of notations, but that's sort of where we're going. So what we're saying is like the full model, this is like a geometric view. So you ignore the parameter, you look at the mean vector. The original regression just assumes that the mean is the image of x. So if you want to do an abstract explanation of what regression is really assuming that the vector observation has a mean which lies in some subspace, which is the image of your design matrix. Once I reduce it, I get a new design matrix. It has an image, and so this new mu hat, which is, sorry, mu A, which is, again, the mean of y. So under the null, we are assuming the mean of y is actually in this smaller subspace. So this is going to be a subspace of this. And what we're testing is whether y actually, the mean actually belongs to the bigger subspace or the smaller subspace. We'll let you think a little bit about this. Is this sort of okay? Too much notation, but it doesn't really matter. The notation you're not going to use usually. Like in practice, you just do what I mentioned. So you just plug in. This is the form, the more general form. So in my slides, I have LA of x. You can imagine that it's just the image of the new design matrix. This is the image of the original matrix. So what happens is that we have this geometric picture. Okay, so the geometric picture tells you what is going on. So full model y is x beta plus epsilon. Reduced model is like y is x z gamma plus epsilon. So this is mu of A. We should change the notation later. This is mu. So this is in the image of x. This is in the image of xz. And this is what your book calls, and I mean in this slide, LA of x. It's not a good notation. And this is also L of x in your book. So L of x is just the image of x. And this guy in image of x z, it's not hard to see. Yes, question.
So Z is just a matrix?
Yes, yes.
So Z is the matrix going to be enforce the conditions?
Yes, implicitly, yeah. So this is implicit enforcement of constraints. Okay. This is explicit enforcement. Because this one, there's no constraints on gamma anymore. Okay, sorry, this is not V, Z. Right, so this gamma is free. The first one is hard because you have to like guess what beta is and then check whether the constraint is satisfied. The second version, I can just plug in any gamma. Gamma is now reduced. So it's like, this used to be d by 1. It's now d minus q by 1. But now gamma is free to be anything. This is like a, usually like, so d is bigger. So it's going to be d by d minus q, right? And once you plug in, you get, this is the reduced model, now gamma is free. I could have done everything in this model, but I have to enforce a beta equal to 0 and solve the restricted least squares. This version is simpler, and usually in this course what we do, it's like this is the abstract version of what we just did. In the simple case that we did, this z turned out to be like just 3 by 1. Because we had d was 3 variables, and then q was 2 constraints. So you get 3 by 1. So did I answer your question, or? Yeah, and then it turns out that it's easy really to see that the image of this is inside the image of this. You write down what the image is. This is the set of all vectors that can be written as x beta. This is the set of all vectors that can be written as xz gamma, but z gamma is just some beta. So xz gamma is of the form x beta. So anything that can be in this has to be in this as well. Okay, so image of xz is a subset of the image of x exercise. As an exercise, try to prove this from the definition of the image. So this fact that this is inside this is like geometric manifestation of the fact that the reduced model is a nested model of the full model. So one model is a submodel, the other one, or nested within the other one in linear regression, means the image of the corresponding model is a subset of the image of the original model, the design matrix, basically. Okay, so each model you can think of linear model as just a subspace geometrically. So this linear model corresponds to this subspace image of x. This reduced model corresponds to this new subspace image of xc. And because one is obtained from the other one by eliminating or by putting constraints on beta, during this sort of argument, you can see that the image of the new, the new subspace for the reduced model is inside the subspace for the original model. Okay. This is up to this point. And then what happens is whenever you fit a regression model, you're projecting onto the corresponding subspace. If you remember the projection idea. So when I fit the full model, I'm projecting this y. We'll move this a little bit above so that you see. So you have y, and this is the y vector. What happens when I fit the linear regression model, the original model, I'm going to project onto the image of x. So projecting down, I get this mu hat, right? So this is mu hat, and then I get the residual, which is e. So e is going to be orthogonal to the image of x, and also orthogonal to mu hat. And I have the Pythagorean y normal squared is like mu hat, and then squared plus e squared, which turned out to fail in the midterm. And so you know that you don't have a proper regression. Okay, now if I fit the reduced model, so this reduced model is just a subspace. Here I'm going to do it a line. So it's inside the image of x. So that's basically in my new notation, this is just image of xz. So this is a subspace in the new, in the original space, is smaller. Could be a line. The other one is a hyperplane. You can see probably, but this is just supposed to be like the boundaries are. This is a subspace, really. It's like a plane, right? And then the other one is a line here. That's my image of x. Yeah, you can see what it is. I'm not gonna. This is the image of xc, sorry, the of x. So when I project onto this, I'm going to project y onto this new subspace. It turns out that this is going to be my, it's going to, the fitted values, which is going to be mu hat of this model, represented as mu hat A here, is going to have to be on this subspace. So it's there. And then the error is going to be E of A. And these two are going to be orthogonal. So you're going to have like a right angle here. And you have a right angle here as well. Okay. So the difference between the sides, so EA is the residual of the reduced model. So EA squared is really SSE of the reduced model. Reduced model. The this is going to be the SSE of M. So I'm going to compare the length of this basically squared to the length of this squared. And you can see that there's a different quantity here, which actually I can do. And I realized that I made some mistake in the previous slide. I'm going to go back and fix it. So we can compare. So you can see that this is bigger. So the SSE, this is the length square of the reduced model, is always bigger than E. And the difference is this part. And it turns out that because E is orthogonal to the image of X, and this quantity, which is the difference of the fitted values, is going to be in the image of X. We'll come back to this, but you can see it's in the image of X. So E is going to be orthogonal to this. So we have a right angle here as well. So a lot of right angles. So this is also right angle. So in this triangle, you look at this triangle, I have EA on the, you know what this is, and then this E squared plus this squared is going to be EA squared. So geometrically, you can see EA squared is going to be mu hat minus mu hat A squared plus E squared. And because this is positive, you can always see that this is always bigger than this, unless things go wrong. And you can see instead of comparing, whenever I want to compare this to that, I can check whether this is small or not. Because in fact, what the F-test is doing is actually comparing this to this value. So the difference basically, which is this, compares it to, I think it compares it, we'll see, compares it to, what do we compare to? The F-test. Yeah, so we compare basically this, which is called the additional sum of squares divided by degrees of freedom to E squared. Right, so what you do is, instead of comparing these two, it's equivalent to compare these two, because they sum to this. And it turns out that if you properly normalize this divided by this, it would be the F distribution. I believe this one is also an F. What I said above is, this properly normalized divided by this properly normalized is F. I may assign this as a homework problem, see if it is F. But what we'll show and what the actual F-test usually is you compare the difference basically. So the difference of these two, which is called the additional sum of squares, which is this guy, divided by degrees of freedom, which turns out to be Q. If you're not wrong, we'll see that. Divided by E squared, degrees of freedom, you already know, n minus P plus 1. Sort of this is related to the S squared. And so that thing is going to have an F distribution under the null. Okay. But it comes from the geometric idea that instead of comparing these two, I can like just look at this. You can compute this directly by just taking the difference of the fitted values, squaring it. This is called additional sum of squares. Or I can like just look at the SSEs and take the differences. That would give me this. But the point remains that this is going to be small if there's not much difference between the two models. So these SSEs would be equal almost. If this is very large, this is much smaller. So this is basically the part of the variance explained by the full model over the reduced model. This is the part of the variation that remains that the full model cannot explain. So this is the variation that remains that the reduced model doesn't explain. This is decomposed into the variation that is picked up by the full model, plus the part that's not picked up by the full model. And if the part that is picked up by the full model is very large, it means that the full model is better. And so you'd reject. So I'll come back to this. There's a lot of like intuition geometrically and statistically about this identity. This is called the decomposition of the variance, sort of leads to ANOVA and all sort of interesting things. But this picture basically summarizes everything. We'll come back next time. You're welcome to look at it and like continue UDF this. Thank you very much.